In Chapter 11, we'll start looking at the carbon cycle. First, we'll look at the terrestrial organic carbon cycle, including organic carbon burial and weathering effects, and the organic leak from land to sea. Then we'll go into the oceans and explore the organic carbon cycle there, looking at the biological pump and upwelling of nutrients as well. Why look at the carbon cycle? Well, all life is based on carbon. Gaseous CO2 is an important greenhouse gas. Ocean acidity is regulated by carbon compounds. The oxygen content in the atmosphere on long timescales is dependent upon the transfer of carbon to sedimentary rocks. There's many paths carbon can take, all of which have greatly different timescales. We already know CO2 is an important greenhouse gas. Even though it's a small component of air, about 400 parts per million right now, it's important for radiation because it absorbs long-wave radiation. CO2 was about 280 parts per million before the Industrial Revolution. Where does CO2 come from, and where does it go? In other words, what are the sources and sinks on a variety of timescales? Here's a classic graph measured at Mauna Loa, Hawaii, at about 11,000 feet, showing the increase of CO2 concentration over time from 1958 till 2004, and it's still on the increase. So we see a broad increase over time with a seasonality too, that it goes up and down every year. So what imbalances lead to the long-term trend, and what seasonal processes help make this line quote-unquote wiggly? First, we'll have to look at carbon reservoirs. First, we have a huge reservoir in the core and in the mantle. We don't need to concern ourselves with that right now. But in the rocks and continents, you have 6.5 times 10 to the 7 gigatons of carbon tied up in rocks, essentially. The deep oceans also contain a lot of carbon, 38,000 gigatons. Fossil fuels, about 5,000 gigatons. Now here we see a discrepancy with what your book says as fossil fuels being the largest deposit of carbon on Earth. That's simply not true. Fossil fuels are typically thought of as accessible organic carbon that we can get to or otherwise usable. And that is about 5,000 gigatons. As you can see, pales in comparison to the amount of carbon tied up in rocks and also in the deep oceans. The biosphere, plants, grasses, etc., have about 600 gigatons, soil 3 times that, the surface ocean about the same order of magnitude as the biosphere, and then the atmosphere too. So the fast fluxes turn out to be between the atmosphere, oceans, and the plants. And then you have much slower fluxes between the bigger reservoirs and other components of the carbon cycle. So ultimately we want to understand how this system of reservoirs are connected and the fluxes between them. And organic carbon is generally thought of as that carbon associated with life processes or biology. Here's an example of some of the pathways of an organic carbon atom. CO2, which is considered inorganic carbon, CO2 becomes part of a leaf by photosynthesis. The leaf can be consumed by an animal, and then the CO2 is directly respired to the atmosphere. That's obviously quite a quick cycle happening in a very short period of time. Or the leaf does not get eaten immediately. It falls, decays, and that carbon remains in the soil for roughly 50 years until it's acted on by bacteria that decompose it and release the CO2 in gaseous form back to the soil, which ultimately seeps to the air. So this represents a slower cycle than the respiration cycle. Or a longer cycle is the leaf isn't decomposed. It turns to an organic sediment in the soil itself, but it's not acted on by the bacteria immediately. The sediment may run via river to the oceans and becomes buried with other organic sediments. In enough time, these sediments become a rock layer with organics embedded within. The plate tectonics could subduct it or thrust it above sea level at some point millions of years in the future. Weathering of the organics in the rocks requires dissolved or gaseous oxygen, and the CO2 ultimately gets released back to the air to finally complete that extremely slow cycle that took millions of years. These proposed pathways represent a part of the organic carbon cycle, which obviously has short and long timescales to consider. So let's look at that graphically. Here we are. We have some CO2 in the air. It gets sequestered by photosynthesis into a leaf. And say this goat eats the leaf. He respires CO2 back. Quick cycle. Or the leaf could fall to the ground. It gets decomposed and turned to CO2 over about 50 years, and it goes back to the air. Or it comes down to the ground. It does not get decomposed, but instead turned into an organic sediment, which runs into the ocean. Here, it meets up with a lot of other organics mixed in with the ocean organic cycle. Given enough time, the pressure of all those sediments will pack it into a rock in a process called lithification. Ultimately, plate tectonics, after millions and millions of years, may someday move that oceanic plate up to the surface, where it can then react with either dissolved oxygen in rainwater or gaseous oxygen, and the CO2 will ultimately be released after millions of years. So the weathering of organic carbon in rocks takes oxygen generally and releases the carbon in the rock to the atmosphere via CO2. So ultimately, this is the reverse of photosynthesis and then organic burial, but the carbon was tied up in rocks for a very long time. So a question is that what is the net long-term effect of having photosynthesis occur without an immediate compensating respiration or decomposition process? Would O2 increase? Would CO2 decrease? Would both of those things happen, or none of the above? Well, the answer is C, both A and B. So if that happened, you'd have photosynthesis happening, oxygen's created, CO2 is sequestered, but there was no compensating process for millions of years. So the long-term effect with that would be for O2 to increase and CO2 to decrease. A notable time in the past where this organic carbon burial happened a lot was what's called the Carboniferous period. So this was a period when Earth's climate was mostly tropical, there was lots of plant life, a lot of photosynthesis going on, a lot of leaves falling to the ground, burying organic carbon and running it into the oceans, making sediments. As that went on for a long period of time, we had more photosynthesis occurring than respiration or decomposition over a long period of time, and this helped build up huge amounts of oxygen in our atmosphere, but at the same time it decreased atmospheric CO2 at that time, and the result at the end of the Carboniferous period was ocean sea levels here shown are going way down, and that's because it got very cold, and a lot of that oceanic water, or at least the freshwater component of it, was tied up in ice sheets during that time. So this represents a very cold period because we were losing carbon to carbon burial, but it also represents a time when oxygen levels went up considerably and started building a large reservoir of oxygen in our atmosphere. So question, the long-term effect that balances this organic leak of carbon or this organic carbon burial is the weathering of organics in rocks. Do you think these two are in balance today? And the answer is absolutely not. The best way to weather organics is not to let plate tectonics take their millions of years and push rocks to the surface where they could be weathered naturally, but instead if you go ahead and dig up those organics and burn them, otherwise using fossil fuels, you increase that weathering rate considerably. So today fossil fuel usage speeds up the weathering process by 1,000,000 times or more. And this really is the fundamental reason why we're seeing an increase in CO2 over time, because as we burn fossil fuels, we're representing an imbalance in that long-term organic carbon. So shouldn't oxygen be decreasing then? And the answer is yes, it is. If you measure it precisely, you do see a decrease. 1 molecule of oxygen is lost for every molecule of CO2 released by fossil fuel production. The difference is the size of the reservoirs. Whereas we only have about 400 parts per million of atmospheric composition of CO2, oxygen, as you know, is 21%. If you express that in parts per million, it's 210,000 parts per million. So if you take away a few parts per million, it doesn't make a big difference. However, it is notable that it's decreasing over time. Our large reservoir of oxygen was again formed millions of years ago when the global climate was tropical and where organic carbon burial outpaced organic weathering for quite some time and built up a large oxygen reservoir. Here we're looking at the seasonality of atmospheric CO2, specifically in the northern hemisphere where most of the world's plants reside because there's most of the world's continents. The growing season is June to October. During that time, CO2 decreases, as you can see. June to October in all these 3 years graphs is decreasing. During the decay season, where there's a lot more respiration and decomposition than photosynthesis, you see CO2 increasing. So from October to April in all these graphs, CO2 concentrations are generally rising. So in the short term, the fast fluxes back and forth between air and terrestrial vegetation is important. In other words, this wavy nature is due to those fluxes between the terrestrial biosphere and the atmosphere. In the longer term, however, it's the balance between the organic leak and the weathering of organics that's important. In other words, the reason why between these 3 years, the average amount of CO2 is going up, the entire curve's displaced upward between years, that's because we're unbalanced in the long-term organic cycle. more artificial weathering by fossil fuel usage than we have organic carbon burial. So again, there's a connection between the short-term terrestrial carbon cycle and the marine carbon cycle. About 0.1 gigatons of carbon a year of organic carbon moves from the terrestrial soil to the seafloor by rivers. This is a small influx into the ocean compared with the oceanic organic matter that falls through the water column. So the oceans have a lot of organics happening there, so let's look at them next. Here what happens is we have phytoplankton that live in the photic zone, the upper 100 meters of water where there's enough sunlight for photosynthesis. So these are photosynthesizing plankton. So they consume dissolved CO2 and produce dissolved oxygen during that process, which are readily exchanged between the ocean and the atmosphere by a process of diffusion. There's zooplankton that consume most of the phytoplankton. So zooplankton don't produce, they can't photosynthesize, but they consume those that do, the phytoplankton. Now the biological pump is the most active part of this, and it ultimately leads to a transfer of CO2 and nutrients to the deep ocean, which ultimately are returned to the surface after quite a bit of time by upwelling. So let's look at this process. You have the photosynthesizers that take CO2 plus water plus a nutrient. They need a nutrient to do this. They make a carbohydrate, an organic, plus oxygen. All that settles, the organic sediments settle down, and what we're talking about with organics here is mostly fecal pellets and organic production, not necessarily the skeletons of the plankton themselves, but what they produce organically. That falls through the water column and gets acted on by decomposition processes. In that process, it simply reverses photosynthesis. It takes the organic plus oxygen, it releases CO2 plus water plus the nutrient to the deep ocean. And ultimately, it's up to the deep ocean circulation to upwell the nutrients and the CO2 back to the surface. So again, this biological pump leads ultimately to a transfer of CO2 and nutrients to the deep ocean, and those items are returned to the surface by upwelling. In the process, though, however, you're creating oxygen at the top level here, and you're removing oxygen at the low levels during that process as well through decomposition. So question, consider that this biological pump is active globally. Given these processes in the thermohaline circulation, where would we expect the most CO2 and the least oxygen in the deep ocean? And the answer would be the Pacific Ocean, because the deep waters of the Pacific Ocean are the world's oldest waters. They've been at depth for the longest period of time, some 600 years or so. That's a long period of time for the biological pump to be pumping nutrients and CO2 down there into the deep ocean. And during that decomposition that happened in the deep ocean, it also removed oxygen. The biological pump effect is relatively small in the North Atlantic since that deep water was just formed. Remember, that's where the bottom waters first form. There's not a lot of time for the biological pump to act on them as a result of them being relatively new water. The deep waters in the Pacific are far more nutritious since they're older, more biological pumping over time. Since the decomposition takes oxygen, those deep old Pacific waters are also oxygen deprived. So it turns out the nutrient composition of the world's ocean is dominated by the production and decomposition of this organic matter, or this biological pump. Shown in the upper graph here is nitrate, which is one measure of nutrients. You can see up here in the northern Atlantic, you have a small number here of nutrients at deep water, and this is the deep water content. It gets more and more as it goes down because the biological pump is actively pumping nutrients to that deep water over time. It gets down to Antarctica, spends some time down there. Some of it upwells in the Indian Ocean. A lot of it upwells in the Pacific Ocean. And that deep water in the Pacific Ocean now has twice the amount of nutrients as the relatively young water in the North Atlantic region. So again, more nutrients in the oldest water. And here's shown as the oxygen content. Relatively decent amount of oxygen in the North Atlantic waters that was absorbed at the surface. Cold water is pretty soluble. It takes in oxygen, then it sinks it to depth. So you have a decent amount of oxygen in the deep water in the North Atlantic. But as the biological pump pushes down carbohydrates down there that are decomposed, that takes oxygen to do that. It starts removing oxygen from the deep water. By the time it comes up in the Atlantic, it's now quite depleted in oxygen as a result of ongoing decomposition at depth. So we come back to this graph when we were looking at chlorophyll concentrations, which is a measure of how much phytoplankton is at the surface of the ocean at any one given time. So it really gives you an idea of how many nutrients are there, because the phytoplankton will only be there if there's nutrients. So things to point out here, Ekman upwelling zones. Along the coast, you get a lot of Ekman upwelling zones. As we know, winds go around Anticyclonically, which means counterclockwise in the southern hemisphere, the Ekman transport is to the left offshore to replace those waters you get upwelling. Same effects for different reasons along the coast of North America, and so there's a lot of upwelling zones. We've already talked about the fact that since there's a weak thermocline and a weak pycnocline in the poles, the winds can mechanically mix deeper waters to the surface, giving you a source of nutrients and lots of phytoplankton blooms that result in that. Also, we talked about the subpolar gyres, primarily up here off Iceland, and also one in the Aleutian area that gives you a lot of upper level divergence and upwelling to come replace that water, giving you nutrients in that process. And finally, another source unrelated to all this is river mouths, where you can get nutrients coming from the terrestrial biosphere into the ocean, coming out here near the Congo area, a big flux of nutrients coming out of the Amazon River, and also the Mississippi and other parts of the world as well. Key points from the organic carbon cycle. There's fast fluxes between the terrestrial biosphere and the atmosphere that dominate the seasonality of CO2. This is more of an effect in the northern hemisphere when we have most of the world's plants there. We'll look at the South Pole record in the future, and there's not as much of a seasonality because they're far removed from most of the world's plants. Organic carbon burial is a leak from the short-term organic cycle into the sediments in the ocean. Ultimately, this raises oxygen and lowers CO2 on long timescales. In the oceans, the biological pump removes surface ocean CO2 and sinks it to depth. Most is returned by upwelling. There is a proportion that doesn't get upwelled or decomposed in the ocean, and that goes on to form organic rocks, along with all those terrestrial organics mixed in there that help make organic sedimentary rocks at the bottom of the ocean. The sedimentation is balanced under natural conditions by the weathering of organics, which lowers the oxygen and raises CO2. However, those things are out of balance the long-term organic carbon cycle. And it's because humans, by fossil fuel mining, pumping, and combustion, have sped up that weathering process. So that's ultimately the long-term part that's out of balance today, leading to an increase in CO2. Of course, we're going to have to look at more small-scale things, like how much is the ocean exactly taking up right now, what are the plants doing, are we getting more plants, and that's for future lectures.